Morning coffee is a harsh, bitter wake-up call, but the paper filter catching those dark drips is also a precise template for elegant geometry. Take a standard 6-inch circular coffee filter. Before it touches the water, it is a perfectly flat, tactile mathematical canvas. If you wanted to find the exact mathematical center of this blank circle, doing it by eye is a guessing game, and doing it without a ruler seems impossible. But we can solve this physical problem with a physical action. Folding the circle perfectly in half creates a central crease, defining a perfect diameter. Unfolding and folding it again in a different direction creates a second intersecting diameter. The exact point where those two physical creases cross is the true mathematical center. Two simple physical actions solve a foundational geometric problem perfectly. With the center located, that single zero-dimensional point becomes the anchor for exploring two-dimensional space. Every subsequent fold into equal angle wedges radiates from this specific coordinate. Snipping small cuts along the edges of that folded wedge and opening it back up reveals radial symmetry. The cuts repeat automatically, creating a pattern identical to a paper snowflake. We can also alter its two-dimensional footprint entirely. By cutting a smaller concentric circle out of the middle, we create a circular ring, known as an annulus. An annulus is a geometric term for the flat, ring-shaped region between two concentric circles. Calculating the area of this remaining paper ring can be tricky. You might logically assume you just multiply the inner circumference by the width of the ring, but that yields the wrong mathematical answer. To get the true measure, you have to find the total area of the large outer circle and explicitly subtract the area of the missing inner circle. Navigating two-dimensional space forces us to account for the void. We have to understand the space that has been removed just as thoroughly as the space that remains. Dimensional complexity increases when we transition from flat paper to a functional three-dimensional object, the cone. Cutting a pie-slice sector and bringing the edges together forces the flat paper to pop up, creating a volume-holding cone. Notice the geometry. The original 3-inch flat radius translates directly into the slant height of our new cone. Meanwhile, the curved outer edge of the flat paper that survived the cut bends around to form the circular base of the new structure. To figure out exactly how much liquid or powder this new object can hold, we face a mathematical hurdle. Determining the cone's internal volume requires calculating its vertical height from the base to the tip, which means applying the Pythagorean theorem. The Pythagorean theorem is a geometric relationship between the three sides of a right triangle, allowing us to calculate a missing length based on the two we already know. A single physical cut into a piece of paper forces us to translate a real-world physical action into geometry, and then directly into an algebraic formula to map out its hidden properties. This leads to an engineering dilemma. Exactly how wide of an angle should you cut out of the filter to build a cone that holds the absolute maximum volume? It is tempting to assume that cutting out only a tiny sliver keeps the base wide, yielding the most space inside. Alternatively, you might think cutting out a massive chunk makes the cone exceptionally tall, maximizing the volume that way. Both assumptions fail the math. Maximizing the volume requires a precise balance between the radius of the base and the vertical height of the cone. This chart plots the cone's volume against the removed angle. As the angle increases, volume climbs, but not forever. The graph hits a strict mathematical peak right at approximately 66 degrees before dropping down. Beyond optimizing volume, this simple circle maps out probability variables when spun on a pencil tip, or visualize rates of color diffusion when soaked in water and ink. High-level mathematical modeling does not require expensive lab equipment. Deep, complex geometry is waiting to be explored right inside the humble, disposable tools sitting on your kitchen counter.